Hey everybody, this video is a recording of a presentation which was made on May 20th, 2021 by two engineers from the U.S. Army Corps of Engineers, Ann Bannett from the St. Paul District and Greg Karlovitz from the Hydrologic Engineering Center. Within this presentation, Ann and Greg discussed multiple sources of precipitation data and their uses within the hydrologic modeling system HEC-HMS. The presentation was made for the U.S. Army Corps of Engineers Mississippi Valley Division Hydrology Statistics and Risk SubCoP. Enjoy!
In this hour today, we're going to be covering a few different techniques in applying precipitation in models. The first one is observed precipitation, where we'll be talking about historic event calibration and kind of a little bit more in line with what we do with SWIMS. From there, Greg's going to be taking over and talking about hypothetical precipitation, where you're looking at hypothetical storms and the methods you'd used for calibrating models and such. And then finally, we're not going to go into a huge amount of depth, but we'll touch on probable maximum precipitation, which is the largest and most intense rainfall that could meteorologically happen in a region. And so all of those, I think, are interesting components of precipitation and is worthy of a discussion on the call, whether you're a new engineer or if you're a seasoned engineer and looking at maybe some of the new techniques or tools available in HMS. All right, moving to my first slide here. When I started out working in St. Paul District, I had a senior engineer, and he always boiled down to pitfalls in hydrology. And he summarized them this way, and I'll just go over them very briefly. One is having a long computation interval. Essentially, you want your time step to be short enough that you get maybe a few points on your rising and falling limb, and his rule of thumb was 1/3 to 1/7 your time of concentration. So rolling that up. Another pitfall is that your design storm is too short, and Greg's going to hit on this in a little bit, but essentially you want the whole watershed to be contributing to your event when you're looking at design and design storms. Third, one of the pitfalls, I think a lot of people in the earlier days especially used to use a SCS unit hydrograph, which didn't really have a customized shape, and so that seemed to be something that was an improvement that we've seen over time. And fourth, to have an uncalibrated rainfall runoff model for synthetic events is a real stumbling block. And that is another area that Greg is going to be hitting on today. And so I just feel really good because we're hitting half of the bullets that this engineer thought were stumbling blocks today. And hopefully this will make us all have something to talk about and get a little smarter. All right, with that, I'm just going to launch into the observed precipitation section. Just to kind of drive home this point, precipitation is really important. It drives the hydrology model. It's critical, whether you're looking at observed rainfall or snow, where you need rainfall and temperature sequence combinations. And then also when you're looking at design events, the hypothetical precipitation event is what we'll be looking at. So with this, you want to consider what is the accuracy of your data. You've got to consider that during calibration. Calibration can reveal bad data sources that should be replaced probably. A rain gauge might consistently deliver poor or low precipitation values or other anomalies. And so you got to think about what is the accuracy of the data that's coming in. What is the spatial and temporal extent? Do the gauges that you're using cover the full watershed or not? Are you missing areas where you could do better by getting more information? And then what is your spatial and temporal resolution? You want the data to be fine enough to give you the detail that you need for your hydrologic model, and maybe tied into this might be the speed of runoff from your watershed or even your watershed size. So just remember, this is an important part of your hydrologic analysis. So what are are some of the observed precipitation sources? I'm going to start with point precipitation here. Kind of looking at what gauges are available, what years do you need to simulate, what is the distribution or spacing of the gauges across the watershed, both within and outside of the watershed, and what's the time step of the data. So when you look at different collections of precipitation, you might find daily, hourly, sub-hourly information. And depending even actually when that calibration window is for your project, you might find that perhaps if you're looking in the 1940s, it might have been just before some of the aviation administration type gauges came into effect, and you'll only find daily gauges. And then what is your strategy to distribute that rainfall over the day that it was observed? And so those are some of the challenges with simulating older or historic events. But you want to take a look at the kind of data you have and how far back it goes, and maybe you want to select your calibration period based on, one, what would be the condition that you're trying to simulate, and then where in time can you grab data. Remember to look at the time step of your data. Some gauges and databases only record them in Zulu. Some of them record them in local time. And if you've got a cooperative rain gauge network out there, what time are they reading their gauge? That time step's important because that will summarize the 24-hour total at their cooperative rain gauge. Other sources for precipitation gauges include rainfall grids like radar that you think about when you see a National Weather Service perhaps on the local network, or other modeled or reconstituted grids. So point precipitation, I've put a website here where a lot of us go to get NCDC data, but precipitation might be coming from local cooperative rain gauge networks. It might come from our own USACE precipitation gauges at some of our projects. But daily, hourly, sub-hourly information be grabbed, and HEC-HMS has and DSS have tools to pull some of these data sets in. So there are a lot of gauges out there, and when you start to look at the database, you can drill down to the temporal resolution that you're looking for, and then take a look at the period of record that's available and crosswalking that with what calibration event you're looking at simulating. Distribution of precipitation point gauges for a model. We go back to that textbook, Basin polygons, where you're looking at perpendicular segments between gauges and then the bisector to define which spatial areas would be assigned to one gauge or another. The top figure is a figure that shows a network of gauges and what that might look like. There are tools outside of HMS in Esri products and perhaps MEPView. I'm not sure on that one, though. On defining what those Basin polygons would be, but essentially the weights that you assign to these gauges and your sub-basin delineations will define those percentages. HMS also has an inverse distance method that is an option to use now, and if you haven't heard of that, you might check out HMS's website in their tutorials and guides to see how that function works. And then also you may consider generating precipitation grid sets from these points. And there has been a legacy product called Gauge Interp that's been around for quite a while. Tom Evans, who used to work at HEC, developed this program. He used to talk about it as being kind of like a circus tent, and each of the precipitation gauges like one of the poles in the tent. And as precipitation values for each time set adjust, those gauges or those poles will go up and down, creating a terrain or a surface to interpolate for each time step. And so the figure on the right shows that same network of gauges we looked at for Basin, but maybe what an interpolated surface would look like from Gauge Interp or MEPView. MEPView also has a Gauge Interp-like processing in it as well. So you can think about that. I'd say from my experience with this, generating some historic time series for about 100 years of record, it was an interesting thing because it seemed like for the periods where we had hourly gauges, it seemed like they were more sensitive to like thunderstorms and lightning, and some would go on and off for a certain period and back on. And it seemed like the gauge inter program and NetView, if that gauge is off for a few hours, it'll simply drop that measurement and interpolate between the other ones around it and then move on. And so it did kind of handle that on-off behavior of some of those gauges nicely. But if it's an extended period, you may want to kind of look at whether that gauge is worthy to include in that processing or not. So gridded precipitation. Now, these are estimates similar to maybe what you'd see from a radar deliverable from the National Weather Service and what they use for forecasting. And the National Weather Service has various stages of radar, and it seems like stage 3 is maybe one that our SWIMS groups are using. Stage 4 is maybe deemed to be a set that has more ground truthing in it. But I would just say be careful when you're using radar to think about the coverage of the radar sensors. And this is a figure we pulled off of the National Weather Service sites, and depending on where you are in the country, there might be some gaps. And so, you know, coming here from Minnesota, there are a few areas that are suspect, but when you are working with radar and working on a project in those areas, you may want to augment or double check your values using point rainfall gauges. So at the district, each district has SWIMS servers and water management professionals who you might want to check with to understand what data sets are automatically coming into their location, and then also maybe what they think have been the best products that work for your area. Data's coming into a central processing center right now and then served up to the districts. And in the new and coming months, a new system called Cumulus is going to be a service that is able to process and data for these precipitation grids on the cloud, and you can define the extent that you're interested in and download from there, and it's supposed to be a little bit faster process. So you know when we use the word Cumulus that this is kind of the upcoming type of processing for the grids coming into the district. There are many different gridded model products, and I'm not going to cover all of them, but I want you to know that there are different resolutions. They're coming from different universities or different products from NOAA. So it will take some investigation if you want to use other data sets than radar, but if you're looking at maybe developing some historical reconstitution and need to reach back, perhaps that would be a good source. I think, Greg, I think maybe you could add a piece here. AORC, I think you mentioned, is one that you've had specific luck with in calibration.
Yeah, that's the analysis of record for calibration. It was specifically developed for helping people calibrate hydrologic models. And so it's a seamless data set that combines satellite, radar, and gauge data together into one product. So far in the modeling applications I've used it for, I've had really, really good luck with it. So, and it's really easy to access, and now with some of the tools in HMS, namely Vortex, it's really easy to pull that in and use it. So that's, of this list, that one I think is going to find probably the most consistent usage for hydrologic modeling.
Great, thanks for adding that. So some of the tools we have for getting grid sets, there is a new grid data importer in HMS. It imports grids from various formats. There is documentation at the website to use those with step-by-step instructions. Generally, you would download data sets from the web and then use the tools to import them into HMS. Again, maybe you want to check with your SWIMS team first, if there are certain products that they already have in-house, but there are new functionalities in HMS to pull that data in easier. HEC also has a vortex utility. Some of those functionalities are going into HMS now, but there's some grid conversion, reprojecting and resampling and clipping ability that came with that vortex. And I think probably the best thing to do is contact either Mike Bartels or Tom Brower, who developed that, just to kind of figure out the current status and the best way to get that, because I don't think it's necessarily downloadable off their common website, going to the public and such. Gauge interp, often that is distributed with some of the HEC training material, but that's a legacy method. It's still out there, but MetView also has a gauge interp-like function where they kind of convert it to a 10 first and then pull it over to a grid. MetView also has some polygon averaging algorithms and volume summaries, which are really nice and quick. And then there's also some functions there for grid adjustments. I would just say MetView, if you're used to the Esri environment, MetView runs a little bit differently, so it's nice to have a step-by-step tutorial in front of you to kind of walk through those steps as you process grids. It's very powerful though. And my last slide here on observed precipitation is just remember to keep your eyes open. Just because you get a grid from National Weather Service, stage 4, stage 3, doesn't mean it's perfect, because they've interpolated some stations into it. And depending on the types of storms, you can think maybe popcorn showers, convective showers, or weather systems are tracking through watersheds. Maybe it's not appropriate to interpolate every point observation across large areas, and so be watching for inconsistencies. This particular screenshot was from Emily Moe working on a SWIMS project, and the stage 4 precipitation showed rain, but her simulation did show that response, but the observed gauge showed nothing. And so with some investigation, she found that the stage 3 precipitation did not have that rain in it, and the stage 4 did, because they pulled in a gauge that maybe was influencing the product that maybe shouldn't have. So use precipitation gauges to check the grid sets even. That's a good lesson to learn out of that. And then also examine storms with viewers like MetView with SWIMS cavities, and then HMS now with their gridded product also has some viewers to watch that storm track and see how it progressed across the watershed. Now Greg's going to grab the presentation and switch to the hypothetical rainfall. I like this slide because Stanford Gibson at HEC says, okay, so if you kind of got off track with the previous section, this is kind of a time to refocus. We're talking about a little bit different thing, and Greg's going to recap here. Go ahead, Greg.
Alrighty. Hopefully everybody sees my slide okay. I'm bouncing between a couple monitors, so I'm doing a little juggling act here. So what I want to highlight is kind of the difference between doing historical storm modeling and hypothetical storm modeling. And really what it comes down to is there's a difference in your goal. If what your goal is to model a storm that happened in the past, usually this is for calibration, or maybe it's for just a number of reasons that you might want to do that. You're going to want to use one of the historical storm precipitation methods in HMS, and I'll highlight which of those precipitation methods correspond to the historical storm. But on the other hand, if you're trying to design something, or you're doing a risk analysis, or there's some other situation where you need to use something that's like a really highly idealized event, then what you're going to want to use is a hypothetical storm method. And so there's a difference here. They've got specific usages. I would never try to model a historical storm using a hypothetical method. That's not going to help me very much. And so just keeping them straight is really helpful, because it'll help you avoid picking the wrong one when you go to do some modeling. So when I say historical storm methods in HMS, what I'm talking about here are the 4 methods: gauge weights, gridded precipitation, inverse distance, and specified hyetograph. The key to these is that they're driven by observed precipitation data. Now, you can get really creative, and you can probably do some external modeling and get some hypothetical storms going and build grids for them, or build specified hyedographs for your subbasins, and feed them in externally. But in general, most people are pulling in products that are an observation of rainfall that's already happened, and what they want to do is they want to model a storm that's already occurred. Of these, I would say right now we're really focusing the most on gridded precipitation, simply because the gridded products are getting so much better and so much easier to use, and they're just more available. I remember back in the day, right? Trying to pull in NextRad data just into a model, especially because the source data was in a terrible format. If anybody ever remembers working with XMRG files, dealing with that, trying to get that into a DSS file, or if you were working in another model, dealing with that as well. That was a pain, and the data were not easy to use. They were not easy to get, and nowadays that's not the story at all. Like nowadays we're dealing with much better stuff, and so we focus a lot on gridded precipitation for that reason. Now, what I'm going to talk the most about here is the hypothetical storm methods. I'm going to talk the most about the one that's actually called hypothetical storm. I suppose this whole bracket of storms could also be called synthetic storms or design storms, because the key to them is they want to model highly idealized storms, and we're usually trying to do design or analysis with them. The four types are frequency storm, HMR 52 storm, the hypothetical storm that I mentioned, and standard project storm. Frequency storm is kind of the legacy one. That's kind of the old way of doing it, and I'll kind of talk about why in just a second. HMR 52 is something that's more related to what Ann will talk about at the end with PMP. Luckily, MVD is largely in the HMR 52 region, so that's all pretty relevant for everybody here, although people are doing projects throughout the country, so it might not always be relevant. Hypothetical storm is kind of our new and flexible way of doing hypothetical storm modeling, and it's got a lot of options that I'm going to talk about. And then standard project storm is only in there if you have to recreate an old study. We only support it for that reason. It shouldn't really be used for anything anymore. And so when we get to the actual modeling, we have to take a step back, and we have to look at our hydrologic model. It's two parts, right? We've got our boundary conditions, which are the rain that's coming into the model, or snow, or whatever we're dealing with. And that's most of what we're talking about today. But it's important for doing hypothetical storm modeling is that you're starting with a calibrated model. The model has to be able to represent the conditions that you're trying to do design for. In most of these situations, what you're going to want to do is you're going to want to calibrate the model to several events, hopefully of similar magnitude to what you're trying to model, so that you have the right parameters that represent the actual hydrologic conditions in that basin. And so it's really important to be able to match those up. A lot of times, one of the things we don't always assume is that time of concentration and storage coefficient, right, our transform parameters, those tend to be affected actually by the rainfall rate. And so when you get to the more extreme events, those values are probably going to change. They're actually probably going to shorten up a little bit. And so the trick with that is if you've got a bunch of very mild rainfall events that you've calibrated the model to, and then you go to do hypothetical modeling, you might be under accounting for the severity of that runoff event simply because you haven't set the model up to match up with the events that you're about to model. I'm going to use a model that I created real quick. It's actually in the Rock Island District. This is a project I spent a while working on, but I always use this watershed as for examples, so I'm constantly rebuilding this model. This is for Indian Creek above Cedar Rapids, so shout out to everybody in Rock Island on that one who's worked on that. But this is a model I was able to calibrate very quickly using AORC data, and I used some default parameter estimates based on judgment and then tweaked them a little bit, and I had this puppy calibrated in about 5 minutes. So that's my shout out to AORC as well. What's crazy about this is the gauge record was really short. There's USGS gauge there that operated for only a few years, and then due to funding restrictions in about 2017 they turned it off. But what that means is when I went to calibrate this, there was really only 1 or 2 flood events that I had. And this is often a situation you find yourself in, is that there's not a lot of these events that you can use. And so it's really up to your judgment to pick the best ones that you have. Now what's funny is I went and grabbed that data and I realized they turned the gauge on like 2 months ago again, and that the East Central Iowa Council of Governments managed to find some funding to get that gauge running again, which makes me pretty happy. The question that I get a lot of is, what are you doing on gauge basins? And in those situations, you're probably going to have to turn to regional parameter estimates. You're going to have to turn to other basins in the area. You're going to have to rely on your experience in order to be able to get parameters that make sense for those. So that's kind of the basin model component of the hypothetical storm modeling. So let's talk about frequency storms, because I think this is probably the one that people have the most experience with. What this is based on is what's called a balanced hyetograph. And what it does is for any number of durations that you choose that are subsets of the total storm duration, it assumes that the frequency associated with every single one of those durations is the same. So imagine we're trying to model the 100-year rainfall. What that means is the 5-minute 100-year rainfall is in there, the 10-minute, 15-minute, 30-minute, 1 hour, all of those, it's built in this staggered block that makes sure that every single duration, no matter what you take, the maximum for that duration corresponds to the frequency. Now that sounds all good, but the problem is this creates really unrealistic storms. It's very, very rare that you would ever see a storm with that type of situation. There's been studies that have shown just how severe that is, and in different places that can be overly conservative more than other places. But the current guidance really is avoid it if you can. You can probably do better with observed storm patterns or some of the other templates that we'll talk about from Atlas 14. I know a lot of legacy things were built and used with this, but one of the biggest problems being that if your watershed's response is most sensitive to the short duration, but it still can be affected by the volume, that it can be just overly punitive by basically calling those both the same frequency. So that's kind of important to keep in mind. So in the hypothetical storm method, which we're going to kind of focus the rest of our time on in HMS, it used to be called the SCS method, and that's because its main purpose was being able to use the 4 SCS storms, and I'll talk a little bit about those in a second. But you're going to notice here that there's 2 other methods in there. There's the area-dependent pattern and the user-specified pattern. And what this basically means is that we took the old SCS storm, we found some other features that were kind of similar to it, and we had to do a little rebranding, and it's no longer the SCS precipitation method, it's now the hypothetical storm method, but the SCS storms are all still in there. If everybody kind of reaches back into their memory, you probably had to mess with these in undergraduate hydrology. The SCS storms, there's probably this little map in your textbook. And really what these are is these are generalizations of 24-hour storm patterns, and they're kind of based on the type of meteorology that occurs. So you'll notice that the most of the country is covered by what they call the Type 2 storm, and that's going to include most of the MVD, and then we'll talk about Type 3 in a second. And those are largely driven by 6-hour type convective events. So they're driven by large, well-organized thunderstorms. And so you'll notice that pattern is really steep. That's because the middle part of the storm is dominated by really intense convective activity. Now, when you go out to the west coast, and that goes up and down the coast, and it changes a little bit, but the 1 and 1A patterns are more atmospheric rivers or pineapple expresses. And so they're more associated with longer duration, and so they're much more mild, they're much flatter. And then when you get Type 3, I mean, if anybody looks at that, they immediately know that's all hurricane influenced. And so it's the areas of the Gulf, it's basically the lowest part of Florida, and then the most exposed parts of the eastern seaboard. And so those patterns, which are really interestingly kind of similar to the Type 2 patterns, but they're driven by observations of hurricanes. And so what these are is they are design storms. They were temporal patterns that were meant, it was originally SCS, the Soil Conservation Service, who is now the NRCS. Their purpose was mostly things like sediment best management practices, so we weren't sending all of our soil to the Gulf. And so they encouraged everybody to do all kinds of practices on their farm fields to keep that from happening. And these design storms were a large part of the method, which basically told them how much runoff they were going to get. They needed some way to distribute these in time, especially for small watersheds where that real short middle duration is really critical to getting the answer right. So those are SCS storms. They live on. They still have their place occasionally. I use them for sensitivity analysis a lot of times because it's really quick for me to just fire up an SCS storm and run it through my model because I have a good idea of what the time pattern means. And in areas where the duration is 24 hours and that's kind of reasonable for the modeling application, it's really not terribly unrealistic for me to use. It can be very severe. It can be very peaked, and that's important to keep in mind. So the SCS storm method implementation in HMS looks like this. It's very simple. You pick which storm you want. So you remember there were the 6 methods. 4 of them are SCS storms, so you pick the pattern you want. You give it a point maximum depth, and we'll get into more detail about this in a second. But there's also an area reduction function. So built into HMS is the TP40 area reduction method. And area reduction is key to getting the answer right. So what area reduction accounts for is the fact that when you have a point maximum rainfall, you don't think that point maximum occurs over a really large area. What you're accounting for is the difference between the point maximum and the area average rainfall. And so TP40, which is an old and I would say fairly outdated document at this point, gave a number of area reduction functions. They vary by duration of the storm area, obviously, and then basically it's a curve, and I'll show these in a minute. But the key here is when you're doing watershed modeling, that the area reduction accounts for the application of rainfall for your whole watershed or for the sub-watershed that you're applying the method to. It's really crucial to use this because these factors can be pretty big, especially for shorter duration storms. Now, for SCS storms, they're all 24 hours, so it always uses the TP40 24-hour curve. But if you vary the duration, and we'll see that in one of the other methods, it'll use one of the other curves for that. But I do want to emphasize just how crucial this is, and I'm going to show an example of this really quick. We've already seen circus tents, and that was a kind of a symptom of the interpolation scheme, as Ann had mentioned before, is you imagine raising the tent pole or lowering the tent pole in the interpolation. But in this situation, just imagine a really idealized storm where there's an absolute point maximum that occurs. Now, it might be stretched out a little bit because the storm moves across the landscape. But as you go to a larger and larger area, you realize that depth has to drop off just because it can't generate that kind of monstrous rainfall over a huge area. I showed an example over here of a storm event that happened basically right over the Illinois River. This was in 2017. But you could see that kind of signature stripe pattern that's associated with really intense thunderstorms. And this is a late season thunderstorm, which is kind of unusual. But in this situation, you can see that they got 4 to 8 inches in that really dark orange contour. I think the point maximum was something like almost 10 inches in the storm. But what you realize is that if you were to pick for your SCS method a point maximum of, I believe, 9.3 inches, and then you were to apply, basically say, all right, I want to now model the entire upper end of the Illinois River. And for anybody who's not familiar, hopefully, I don't know if you can see my pointer here, but the Illinois River, it starts at the Des Plaines River, and then it just kind of generally flows southwesterly this way, like right along these contour lines, like parallel to them. If I had the watershed lined up with that, I wouldn't want to use that 10 inches rainfall everywhere. That describes the absolute maximum that happened. But if I knew the area of the storm that I wanted to model, I can use a depth area reduction function to get down to what that area average should be. And so I can actually account for the difference in this point maximum, which is probably somewhere in here, out to the area average that covers a much larger space. And these are crucial because these, I'll show in a second, functions. It can reduce the rainfall pretty severely, especially in large areas. So these are the TP40 curves, and there's a lot of baggage here, and that's why I really want people to be cautious with these. What you'll notice is that they vary by duration. So the top curve is for 24 hours, and it goes down to 30 minutes, which is the steepest curve at the bottom. You'll notice that the analysis here stops at 400 square miles. Now, these curves aren't asymptotic. That is the #1 misapplication of these curves. 24-hour does not approach an asymptote at 91%. So what these curves are, let me back up for a second here, is the relationship between the area of the storm and the ratio of that area average to the point maximum. So obviously, if you're just looking at a point, they all come to 100 because the point and the point, that's a ratio is 1. But as you get average more and more area of that storm, you reduce the point maximum to the area average. So for 24 hours, it's going to be the slowest because you've got more time to accumulate rainfall and it's not as flashy. But if you look at a very short-lived thunderstorm or very intense event, you'll notice that that reduction is really severe. And it stops at 150 basically because they didn't have any data. There weren't enough gauges for them to really get out to large areas like that. A lot of these were in high-density experimental gauge networks like the one that used to be set up in the Chicago area. But the #1 misapplication of these is that they're asymptotic. The 24-hour does not just approach an asymptote and say, oh, it's 91% out to whatever drainage area. 6-hour doesn't flatten out to 83%. I've seen that a number of times, and I really want people to be careful with that because what this actually is, they stopped the analysis at 400 square miles. And so when they drew these smooth curves in, they flattened out to grab the points that were at that end there, and they didn't have any storms bigger than 400 square miles in here. So if you do need to average over an area bigger than 400 square miles, you're going to have to develop your own depth area reduction function for that. And you're going to do that based on observed storms. And that's kind of beyond the scope here, but there are tools for doing that in METView. So if you have observed storms, you can turn those into DAD tables. And that's really important to know. Depth area analysis is so important that we have an entire simulation type for it in HMS. When you do hypothetical modeling, one of the parameters is almost always the storm area. And one of the shortcuts we usually use in hypothetical modeling is to set the storm area equal to the drainage area. And so basically you're imagining that the storm has some real odd shape that exactly matches the drainage area of the watershed you've got. And so it's a real simplifying assumption. But for design, it's usually sufficient. And so what the depth area analysis does is it lets you choose for a basin model a number of points that you want to analyze the storm at. And what it's going to do for each of those elements is automatically compute the drainage area above that point. And so when it does that, it'll automatically apply the area reduction function that corresponds to the drainage area above that analysis point. And so I haven't seen a lot of people use this because I just don't even think they're aware it's there. When I start doing things or thinking about studies like FIS studies or trying to generate profiles where I need frequency flows all the way down a river, this becomes very, very important because it automatically adjusts my storm area for me as I go downstream. So it's really important to use. So if you've got notes turned on in HMS, I know we recently added the feature to be able to turn notes off, but sometimes when I'm doing modeling like this, I turn it back on and it's kind of noisy. HMS is pretty chatty. But for this simulation, I basically set up a depth area analysis, just like the last one showed, and I have 2 analysis points in there. The point maximum was about 7.5 inches. That corresponded to the 100-year storm from Atlas 14. But what I did is I have 2 analysis points in there, and it automatically computed for analysis point Marion that the storm area above it was 67.5 square miles. And so then what it did is it went over to the TP40 curve, got the area reduction value for, I believe this is a 24-hour storm, and then it applied it at 67.5 square miles to reduce 7.49 down to the area average of 7.06. Then it went further downstream all the way to the outlet of the watershed at Cedar River, where the storm area now is about 93 square miles, and it reduces it further to just under 7 inches. So you can see how you start with that point maximum, and it goes all the way down. You know, it's lost a ½ inch, and we're not even at 100 square miles yet. So one of the features in the hypothetical storm is called area dependent pattern. This was developed for an external partner. It does have some usage. It's a little bit of a kind I would call a power user feature. There's some applications that this is really useful for, but I wouldn't focus on this one as much. It's got a lot of the same settings where you're specifying things like the point depth and the area reduction. It also has controls for the storm duration. It also lets you specify a storm temporal pattern that corresponds to the storm area. And the reason this is because this was entirely designed to be used with the depth area analysis simulation type in HMS. So if you find yourself in a situation where you don't think the storm pattern, the time pattern that you want to use, is accurate or relevant for the drainage area that you're working at, you can specify different storm patterns that correspond to different storm areas and use those. And that can be really useful if you've got observed storms that you want to use. And when HMS does the depth area analysis and it marches downstream, it'll interpolate between those storm patterns that correspond to these areas. So a little bit of a power user feature, but definitely something that's flexible to use. So the storm duration is kind of a tricky topic because that's a setting now that we're getting into here. And the guideline I'm going to give you is to choose the shortest friendly duration longer than the time of concentration of your outlet. The friendly durations, I would say, are the ones that are in Atlas 14. You'll see them, I'll show a table in a second, but you'll see a number of durations that are in there, and they're usually at kind of convenient analysis points. Choose the one that is the next longer than your time of concentration of your outlet. That's the simplest guideline I can give you. Another school of thought on this is that you can analyze the critical duration for your modeling objective, and we'll talk about critical duration in a second. But that might be different than your time of concentration, and you might find that there's a duration of storm that changes your answer more, and you want to know what that is. But there's definitely more guidance needed on this, and something we've been trying to work on over the last couple of years is getting a proposal funded for us to do research on hypothetical storm, basically application guidance. We've had some trouble getting it into the R&D queue, and so one of the things that I'm kind of putting out there almost as a sales pitch is if this is important to your projects in your district, come partner with us and we'll figure out how to develop some guidance on this. And I'll have a pitch about 2 other features like this in a couple of slides here. So critical duration is kind of a contentious topic because it's been used in quite a few circles, meaning slightly different things. But in this context, what I'm really talking about here is usually flood peak modeling. If you're imagining trying to get a flood frequency curve from rainfall frequency, there's a couple of schools of thought here. One of them is you take the same frequency, say the 100-year, and you use multiple durations. So say you use 6, 12, and 24 hour. And what you do is you run them all and you get the worst, choose which one's the worst result. So if you're modeling floods, you choose the one with the highest peak. So bearing in mind that your time patterns might vary with duration, obviously your depth is going to vary based on that duration. The DAD might change based on those durations. So with so many moving parts, sometimes the only way to do it is to run them all and find out which one's the worst. My favorite way to do this is choosing a duration tied to the meteorology. So I do a lot of precipitation frequency analysis, and one of the things that we've worked on recently is how do you characterize different types of meteorology and their basically characteristic storm durations. And what we found is that for areas that are dominated by convective storms, when you look at convective storms, the effective period of their precip is about 6 hours. And so you could just ignore the watershed conditions and pick a duration that's basically relevant for the storm that's dropping it. And we can have more of a discussion about that, but that's been our kind of our meteorology first approach to that. And then the other school of thought is to do a sensitivity analysis of storm pattern and duration, and don't pick a single storm duration and display the results and show the uncertainty that's caused by the storm duration. Because in real life, storms happen at a number of durations. It doesn't, it's not always just going to, every time in your watershed, rain for 6 hours. And sometimes it's good to know what the range of the possible responses is. I do want to talk about time patterns real quick. In HMS, time patterns are entered as percentage curves. It's not. There's a couple other things that have the word percent in them when you go to pick a paired data, but the one you want is percentage curves. And the C part of those should be percent in the DSS path, and the X and Y units should be percent. If you manually enter one, it'll automatically handle that for you. If you link to a DSS file, you got to make sure those line up. So this is an example of a couple of time patterns that have been done in the area-based storm. You can kind of see here that when the precip was sampled and run through that area-varying storm, that for the downstream element, which is in dark blue, it used a different pattern than in the upstream element. So that's just a feature that that can be used to kind of make those relevant. So I do want to be cognizant of time. So one thing I want to do real quick here, I do want to highlight where you can get these time patterns, and those are NOAA Atlas 14 has temporal distributions for all the areas it's covered. I encourage you to explore the website and try those out and take a look at them. But I do want to make sure you know exactly what you're looking at. So what it does is it divides up the patterns in two ways. One of them is by quartile, and one of them is by percentile. And what they are is a quartile tells you basically what period of the storm the most rainfall occurs in. A first quartile storm happens in the first quarter of the storm. The second quartile storms in the second quartile. That's how that works. Now what the percentile is it's basically the range of uncertainty for a quartile. So the plots I'm showing here are dimensionless mass curves for one of the regions in Atlas 14, and it's for a 24-hour storm, but these are all the second quartile storms. So that peak happens somewhere between 25 and 50% of the storm duration. And you'll notice that there's 9 curves in here. That's the 10th through the 90th percentile. And in these situations, what you're basically saying is that the 10th percentile is the fastest accumulating storms. They hit that quartile peak the fastest, and the 90th percentile are the slowest accumulating. That still gets you to that second quartile. So there's a lot of uncertainty in these patterns. These are from a huge analysis of storm patterns that occurred. If you go into Atlas 14, and I would really recommend reading the actual documents. There's a lot of really good stuff in them. They did an analysis of a huge number of storms. And one of the things that if you really don't know what to pick is you can just play the numbers game and look at some of these and say, oh, I'm going to go get the ones that are most likely or most reasonable for my region. And so reading the document will actually be insightful about what that is. This is kind of topic number 2, where we want to partner with everybody out there in the districts and figure out what we can do to make better recommendations for using temporal patterns. Right now, the guidance would really be to do a sensitivity analysis, but I'd like to help develop more concrete guidance with examples for everybody. So finally, I'm going to get here to the user-specified pattern, which is the last precip method in the hypothetical storm. In this one, you're going to notice here there's the smorgasbord of options. The biggest things to notice in here is that there is a sub-option for precipitation method in here. You can use the traditional point depth like all the other ones, but this one also lets you use precipitation-frequency grids. What that means is you can directly take a grid from Atlas 14 and HMS will do the spatial averaging for you, which is huge because that eliminates any external work that you would have to do in GIS. As long as you have a georeference model and it's got sub-basin polygons, it can figure out what the average frequency depth is for the frequency grid that you give it, which is really cool. Otherwise, it lets you specify a time pattern, a duration. In this case, it lets you pick one of the precip frequency grids, and then it's obviously got the area reduction functions because it still has to make that point to area adjustment. Precipitation frequency grids have a little quirky setting to them that you do need to pay attention to. You can create the grid in HMS, and it's called a precipitation frequency grid, but when you import it, you can link it to an ASCII file, which is exactly how Atlas 14 provides them. And one of the settings in there is the unit scale factor. And this is a big pitfall here you got to watch out for. is you have to know the source data's scale factor. It's buried in the metadata, but I can tell you this, that if you're using Atlas 14, they're stored in inches and they're stored in thousandths of inches, which means the unit scale factor is 1,000. If you're unfortunate enough to be stuck with Atlas 2 somewhere in your project, the scale factor is a completely unexplainable 100,000. I don't know why they chose that, but that's what they did. The reason scale factors are used is to make the grids all integer values. They don't want to store decimals. And so with these scale factors on them, they store integer values, and then when it's read in, it's assumed that you divide off that value to go get to decimal values. So when you link to an existing grid like this, especially those ASCII grids from Atlas 14, make sure you set that unit scale factor correctly. So I was going to show a little bit of a highlight of the Atlas 14 website, but what I would recommend is that you go play with that for yourself. There's a lot of great information out there. There's a lot of tools. It can be kind of overwhelming. But the point I really want to drive home is that Atlas 14 might be the most misunderstood data used in hydrology today. Everybody's seen this table, I think, in one form or another. Either it's from Atlas 14 or something like TP40. It's basically down the columns is constant frequency, across the rows is constant duration, and then you want to say, I want the 100-year, 24-hour storm, and then you basically go down the 100-year, you go to 24-hour, and you get your 7.49. That's all fine and good, but all that tells you is what it happens at a very point, because remember, precipitation generally is measured at the point level, and it's important to remember that, because we just had this whole discussion about area reduction. And what I see people do, and I want to caution you against this, is you go and you get the ASCII grids and you treat those as the pattern for the 100-year storm, and that's not what they are. The maps were only created so you could drop a pin anywhere in the map and at that very point get what the 100-year 24-hour rainfall is. So when you do this, make sure that if you do use those grids underneath it, that you are using area reduction, because this is telling you what the point maximum everywhere is. It's not telling you what the area average is. So that's really important to consider. So please, please, please be careful with that. Spatial patterns right now in HMS, the rainfall is only being applied uniformly. And for the situations that we typically encounter, especially for things like FIS hydrology, it's probably okay. For really big situations, either large watersheds or what I would call hydraulically complicated, that involves things like dams or diversions and things like that, it's not always a good assumption, and you might have to do something special, and you can always come talk to us, and we'll try to guide you through what to do on that. But for now, it's all uniform, and that's important to keep in mind. So I'm going to end this with a sales pitch. Of course, I'm not a very good salesman in general. I've never worked a sales job. I worked retail, and that was miserable. But what I want to talk to everybody here about is that the districts are using this stuff. We're trying to build the tools to help everybody get their projects done as well as they can, as fast as they can, as accurately as they can. And we've got a big gaping hole right now. Hypothetical storm modeling is kind of the Wild West. A lot of times it's ad hoc advice that we can give you guys to get through this. But we need to develop modern guidance, and it needs to be cohesive, and it needs to be relevant and applicable for the districts. And so really what we want to do, we, HEC, I'm kind of speaking on behalf of the center right now, is that we want to work with the districts to help develop best practices. And the three keys right now, and so if you've worked on this stuff and you've got an interest, please contact us and we'll see what we can do here, is the duration of storms for hydrologic applications, the temporal patterns that we should be using, and how and when spatial patterns are important and what to do in those situations. So those are kind of the keys. I know there's other issues that are out there that people have encountered in projects, and they've come up with all kinds of inventive ways to solve them. And I credit the ingenuity of the districts in doing that, because you guys are on the ground getting these projects done. What I'd like to do is take those lessons learned and figure out how to get that out to not just your district, but everybody else as well. So please partner with us. And I apologize for running over. I got a little chatty there, but we got to get back on the train so that Ann can talk about PMP.
Awesome. Thank you, Greg. That was awesome. And hopefully you can see my screen. We're back to the third topic of today, another kind of precipitation consideration. And we'll do it in a pretty high windshield version of the discussion, maybe just focusing on the precipitation and where it comes from itself, but not really applying it in the model. That we'll probably have to have another presentation on that, something like that. So probable maximum precipitation is a theoretical greatest depth of precipitation that you might have for a given duration over a region, a particular area. And its PMP is the acronym that people use to refer to the probable maximum precipitation. It's really used as a design storm, maybe for formulating a project that, or a spillway design, or looking at dam safety considerations. But it's good to know that the precipitation estimates for the PMP are really based on regional information and historic storms, where a meteorologist has been involved to help maximize the storm. They call it essentially looking at the storm itself, and if you were under optimal condition, how much more would that storm have dropped? Transposition, meaning could a storm, a regional storm, if it would have moved and delivered a storm elsewhere, how far could that storm have been applied? You know, there are probably physical barriers like mountains or other orographic effects that would help to winnow in on where that storm could likely travel. And then envelopment, essentially, because we don't have data everywhere, we're looking at these techniques to move and maximize storms, and then develop an envelope of what those maximums might be in other areas. So it's kind of a combination of historic storms and then kind of a optimization. The guidance for PMP in the Mississippi Valley Division would generally say that you'd be looking at HMR 51, 52, 53. There are a couple exceptions in the way northern part of the watershed where we're dealing with snowmelt, and there we've got HMR 48, which was written specific for those two watersheds. But I do want to point out that these HMRs were written and published several years ago. And I would say John Denver may have been very popular in the music scene in some of these documents and delivery dates, but it's something to be aware of, because when you get into a study, you may want to consider looking at some updates. So I'll go on and move forward from there. The idea is that PMPs were developed back in the era before we had GIS technology, and they were looking at envelopment and transposition and regions. And so I'm just going to kind of quickly go through. There's a lot of background information, but they did take historic storms. And then you can see on the figure on the left, there are a whole bunch of storms taking a look at the depth, area, duration relationships for all these different storms. An envelope is developed, which is the heavy red line, to define kind of that smooth relationship that would help define what kind of maximum storm could possibly happen in a given watershed or region. So again, these are regionally derived and based on some historic events. And so to kind of summarize, shows 5 factors that are really important to consider when you're developing a PMP for a specific region. Storm area, the spatial pattern, the temporal pattern and how that precipitation is applied, the location of the storm over the watershed, and the storm orientation. And essentially you're looking for the best combination of all of those different factors that will create the largest impact on your study area. For example, on a dam, what is maybe the combination that would produce the highest volume or highest stage in a given reservoir. HMS has a relatively new feature, HMR 52. I think it first came out in version 4.3, but unless you've been working on a PMP recently, you might not know it's there. Essentially, they're applying HMR 52 probably in our division watershed, so that makes great sense to use this. It has a storm optimization tool. You'll have to have the watershed elements referenced in HMS with the GIS operability, and then using index maps from HMR 51, you enter different relationships that define the precipitation that could possibly happen in your watershed. And then the tools in HMS will help optimize the centering you can specify maximize the flow, volume, or reservoir stage. And so be sure if you get into a PMF analysis that you take a look at the training available for HMS in this regard, but there is that tool and it is a huge time saver. So kudos to HEC for getting that in there. And then, as I said before, if you're faced with updating a PMF and you need to look at PMPs and you remember this presentation like, oh, these are kind of outdated documents, I'm not saying that they're bad everywhere, but I think it's worth looking at whether there has been a really significant event in the region. And then I would consult with a meteorologist, hydrologic hazards team member, maybe Greg, go right to Greg and get some insight on there. You know, are there recent updates in water? Certain parts of the country have had updates in their PMPs, and North Dakota is one that's finishing one. I think maybe in Texas there was something recently. I'm not the expert on the whole division, but probably should be researched. There is a person, Chuck McWilliams, at the Omaha office who's been my go-to person. He's involved on the review panel for a lot of PMP updates, and it really has a good know on what's happening out there in the country. He's also kind of the one, his group helps keep the extreme storm database updated. I don't know if everyone knew that existed, but Doug Clemenson, who has retired from the Corps, but he was from Omaha, he was kind of the father figure of pulling together these extreme storms into a database. And that's accessed by Chuck McWilliams' group to look at other extreme storms and lay them out. Again, analyzing the storms with the maximization, the transposition limits, and then taking a look at the depth, area, duration curves and the envelope to make sure, you know, that the storms are still fitting in that envelope in HMR 52, or perhaps there are segments of that curve that could be adjusted to reflect the more modern storms. Another word or study that's used as a site-specific study, and that was really a super in-depth investigation of meteorological drivers for PMPs. And so all of that is kind of wrapped into this umbrella for PMP. And like I said, Chuck McWilliams has really been my go-to person on that. But there are resources on the web. There are different tutorials for all of the precipitation topics we talked about today. HMS Discourse has a lot of information if you do some searching there. There have been some recent training, both for dam safety, and then I guess in 2018 there was a RMC periodic assessment webinar where various topics were covered, and that can be reached on ProjectWise. Phew. We covered a lot of information today. Are there, I guess, Mike, are you seeing that there are specific questions that are coming up in the chat that you think we should be addressing right now?
Just got the first one, actually.
Okay.
Can you go ahead and say it out loud, John?
Sure, yeah, sorry, I had to find the mute. Yeah, I was noticing for the SCS storm type map, it looked like Puerto Rico was shown with just a clear background, like that would be SCS type 2, but you had mentioned type 3 as being used in the hurricane zones, like along the coast and the south, so I wondered if that was correct, that Puerto Rico is type 2, or is that just something that hasn't necessarily been studied closely enough or factored into it, you know?
Yeah, I see how you interpret that in the plot there. I'm looking at it right now. I can't speak for the original intent of the document. Luckily, those patterns are fairly similar, that if you were to apply one or the other, that the difference is not huge. Based on that reasoning, I certainly would pick a type 3 storm to model Puerto Rico.
All right, thanks.
So yeah, I do want to get to this question from Carrie. She asks if there's any expected guidance updates related to this information, and that's kind of what we're hoping for. We don't have it we don't have a timeline, we don't have funding or anything like that. And really, right now, what we're hoping to do is find some avenues to get that time funded to work on it. Like I said, we're gathering up the lessons learned from the districts, gathering up what I've worked on for the last couple of years and other stuff that people have done, and we want to roll that into some guidance, but unfortunately we don't have a vehicle for that right now. We've tried R&D, so far not so good. We've considered headquarters GI, and that might be something worth proposing, especially if there's somebody in the district who wants to work on that. That'd be great if they wanted to submit a GI proposal to work on stuff like that. So we're beating the streets right now a little bit, trying to find, number one, money. That's obviously what makes the world go round. But the other part too is other people who want to work on it, who have the experience and the interest in doing it.
This is Don Duncan in St. Louis. The current HMS technical reference manual basically says if you've got time of concentration of your basin less than 24 hours, you should just use a storm duration of 24 hours. What I heard today maybe makes it sound like you should do a bunch of sensitivity around that. And when you say the worst storm, is that, I guess that is project dependent?
Yes. Yeah, so the technical reference manual, I mean, that's another document that definitely needs some updating. In this situation, okay, let me step back. 24 hours is probably the most reliable analysis duration we have. The reason we fall back to that so much is because the bulk of the precip data that we get is 24-hour. We get sparse observations of hourly, and so we're not as confident in those things. And so a recommendation for a long time was, if you can, use 24-hour for everything. That's why it's so focused on stuff. The recommendation I would use today is, yes, check what makes sense for your watershed, especially if you're working in those smaller watersheds where the timing might be a sensitive parameter. You might find that going shorter is important. Now, that may mean having to gather area reduction information for the duration of interest. And one of the convenient things about 24 hours, the TP40 24-hour curve is in there. So it's kind of a trade-off in terms of what information you might have at hand. But yeah, my recommendation would be test the watershed for sure.
Okay, and then as far as temporal distribution, you said avoid frequency storm if we can. Is there what would be the second best option for now, as far so we're not going overboard with testing every possible combination?
I would go to Atlas 14 and I would find, at least to narrow it down by quartile, find the most common quartile in the region that you're doing. There's a map and everything. As long as the area you're working in has been covered by Atlas 14, there's a map that'll tell you which, they call them temporal regions. Check which one you're in, and then there's a table that'll tell you, I had it in the slides, and I'm sorry I kind of blew over it. I could throw it up there real quick, but I'm going to steal the share back here if I can. I know we're running over a little bit, so I'm hoping people are okay with hanging on for just a second. So there's a table that looks kind of like this. This is for, I believe, volume 8. So you got to check which area you're in, and they identify 4 regions. There's a map for this, so you don't have to guess which one you're in. But for the area I was just working in, I found that, okay, 24-hour made the most sense. I'm in region 1. When I go to see which quartile my storm is in, most of the storms are first quartile storms. So I feel pretty good about picking a first quartile storm to do my modeling. Now, in the situation of which then percentile do I pick, what I usually recommend to people, especially for flood modeling, is if you have to pick one, pick the steepest one. If you can't afford to run a few, run a few. Because we've found that in a couple of places we've tested this, that unexpected ones have been the most severe, and which is why sensitivity analysis has kind of been the recommendation so far. So the key is go look at Atlas 14. This is in, I believe, like Appendix 5. The document's available through the website if you go poking around. And it gives you a good explanation of how these were analyzed and kind of what they mean. But at least this will narrow it down to a quartile, and that gets you just a handful of patterns. And I do have a resource for temporal patterns if you're in a sticky situation where you don't want to load all those in. It's pretty quick to pull those into your model and then just flip through them in a hypothetical storm if you want to try running them.
All right. Well, I know I feel a little smarter now that we've heard all of these presentations. And Greg, I thank you very much for joining up with me and helping share this information across the valley. Thank you. And Mike, thanks for being our back wing person out there to field questions and help with that as well. So, yay. Thanks, Greg.
Thanks for having me.
All right. Have a good day, and thank you for joining us.